Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Today we're going to be finishing out the nature of what the hydrogen atom is and the models of the atom through history. So let's take a step back. Last time we looked at Rutherford's version of the atom, which is kind of like little stars orbiting a little planet, little planets orbiting a little star. That's the kind of basic assumption that Rutherford came about when he did his gold foil experiment. But if we go back just a little bit further back in time, we find that there's a very interesting hint to things to come. The Swedish physicist Johannes Rydberg in 1888 looked at the nature of the hydrogen spectrum and tried to create an empirical formula. This empirical formula had a goal, and the goal was to actually simply model the actual lines that are seen, the transitions that are seen, or at least the spectral lines that are seen in the hydrogen spectrum. So what he did is he found a periodic pattern to them, and he was able to determine that the reciprocal of the wavelength is equal to some constant, some full constant, and then multiply it by the reciprocal of the inverse of two squared integers. Now this is really interesting because it highlights a concept that what you sometimes do in science is you just try to create some sort of empirical formula for what you're observing in nature. And after you do that empirical formula, you then try to see if you can understand the underlying science below it. Well, that's what Rydberg did. He made an empirical formula that is only based off of the data, but he had no underlying reason as to why it would be this way. He just made a formula that worked. Fascinatingly enough, the Rydberg formula for the hydrogen atom is extraordinarily simple. So what it should tell us is that we are looking for underlying physics that actually works to tell us something deeper. And that was in 1888. So many things were happening right around the turn of the 20th century, 19th and the 20th century in terms of modern physics. It's astonishing. But Rydberg's hint gives us a little bit of a clue. All right. So let's go forward in time from 1888 to 1911. And 1911 is when Rutherford came up with his concept for the atom. And it was needed to be done because the Thomson's plum pudding model doesn't work. Well, Rutherford's model of the atom also cannot work, and it can't be the last answer to things, because if you have an electron orbiting a proton, and the very active it going around in a circle is an accelerated motion. If you have an accelerated motion, you're going to emit energy, and by emitting energy, the thing will eventually spiral in. The electron will spiral in, emitting electromagnetic radiation. As it spirals in, and it'll crash into the proton and become Thomson's plum pudding. So the Rutherford's model of the atom could not actually be the final answer because extraordinarily well-established electromagnetic theory demanded that they would eventually collide together. So something else had to be there in order to make this work. Well, that came along because very shortly thereafter, in 1913 by Niels Bohr. So what Niels Bohr did is he said, okay, fine, we don't want this thing spiraling. Fine. Imagine that the angular momentum of the objects was fixed. And so what he did is he said, okay, every one of these little planets that orbits this little sun, they can only orbit at specific radii. So if he said that's his basic assumption. The basic concept is that they can only orbit at specific radii and they can't spiral in. Well, why can't they spiral in? That's the essence of the Bohr model of the atom. The Bohr model of the atom said basically that the angular momentum had to have fixed values. And these fixed values were integer multiples of some value. So that's his idea, is that Bohr's model of the atom said we could have quantized angular momentum. And what is angular momentum? Well, if you take a little planet orbiting a little star, and the angular momentum of the little planet orbiting the little star is the mass times the speed with which it's going around, times the radius at which it's going around. So if the angular momentum is quantized, then, well, you know the mass, fine. You can determine the speed, sure, but then the radius must then be fixed. There must be only stepwise distances that the electron can live from the proton. So the Bohr model of the atom says, let's now take this concept of quantized angular momentum. And what we'll do is we'll say, what is the force that is required to keep something going in a circular orbit and then equate that to the force due to the electromagnetic attraction between the electron and the proton, make those two things equal, slide in the concept that the product of the mass times the speed of the electron going around in that circular orbit at the radius of the circular orbit is some integer multiple of some number, and that number is the Planck's constant, the reduced Planck's constant h bar. And you get out of that by doing some hooks and some crooks and looking and playing around with it. You eventually discover that the energy at a given level that you would have. So if you have a potential energy between the electron and the proton, so they're trying to pull on each other. So that gives an energy that is of position, and that we call a potential energy. So the potential energy between them is fixed. And we can determine what it is, and it's dependent on the radius and how far apart they are. And we say, okay, what is the energy at a particular location? And it works out to be a very small amount, which is in electron volts, about 13.6 electron volts is the amount of negative energy, or energy that's different from when the electron is free. So it loses a bit of energy getting close to it, close to the proton. So it can only have energy at fixed orbital radii. And these orbital radii are integer multiples, or a product of the orbital number squared. So the ground state, which is the lowest possible state, which is n equals 1, that is the lowest possible state. And then you can have larger and larger and larger n's, but they just get bigger and bigger, which means that the energy approaches 0 as you have greater and greater distance from the proton. So the Bohr model of the atom, by having quantized angular momentum and using the definition of the potential energy between an electron and a proton, and the definition of a force that's keeping something in a circular orbit at a particular quantized angular momentum, utilizing the Coulomb relationship, which is the force of attraction between two charged particles, we can then derive with Bohr's concept that the angular momentum is quantized. We get a very interesting set of results. So first, the electron could only live in fixed orbital radii from the proton. And the nearest one is when this fixed number is 1, or this quantum number is 1. And if it's at quantum number 1, we call it the ground state. If it's quantum number 2, we call it the first excited state. If it's quantum number 3, we call it the second excited state. So an electron can only jump up and can move between energy levels. So these are levels of energy, fixed radii from the proton. And so we have an electron either at the ground state, at the nearest radius, or at the first excited state, which is at the next radius up. Now, something can come along and smack the electron. So let's posit now, as we will, how we can use the Bohr model of the atom. So let's have an electron orbiting a proton. It's a nice little hydrogen atom. It's sitting out there somewhere in space, not doing anything. It's minding its own business. And another proton comes along, or another hydrogen atom comes along, smacks into it, and gives it a little bit of energy, just like a billiard ball by smacking another billiard ball. It makes a little clicking sound, but instead of clicking, what happens is a little bit of that collision goes to making the electron go up in orbital. It kicks it up to the next orbit. So a collision can do that. Gives it a little bit of energy. When it gives it a little bit of energy, it can jump a little bit further away from the proton. So now it's gotten some energy. It's pushed away from the proton, which is trying to pull it home. And it says, eventually, this state can't live for very long. And what happens is the electron then says, I'm going to go back down to the lower level, from the first excited state down to the second. And in so doing, emits energy. Now, it can do this emission of energy by, say, colliding into something else, but probably the most efficient way and the most common way is for it to emit light. So when it drops from a higher energy level than the ground state down to ground state, it'll emit a light. It'll emit photon. And that photon will have exactly the energy of the difference between two levels. So let's see what that actually works out to be. At the ground state, the energy that you have is about 13.6 electron volts. And we're going to call that a negative energy because if let's say the electron and proton are not bound together. If they're not bound together, we would say they have no energy with respect to each other. So they're free. So a free electron free from its proton would have zero energy. And we call bound states negative states. So you can think of them as at the bottom of a well or the bottom of a hill or something like that. So they have to fall into this potential well. And so that's where we get the negative state from. So the energy, we're going to call it, is a negative 13.6 electron volts. And I'll let you Google what an electron volt is, because that's a really interesting subject all of itself. So that is n equals 1. And that has an energy of 13.6 electron volts. So now if something comes along and collides into it, the electron jumps up to the next orbit. So that's at n equals 2, and that works out to have an energy of minus 3.4 electron volts. It then emits an electron, it emits a photon as it drops from the first excited state back down to the ground state. And you subtract the two, minus 3.4 minus a minus 13.6, that ends up to be 10.2 electron volts. That's a very small amount of energy. It's on the order of 10 to the minus 19th joules. So it's a tiny amount of energy. Well, you'd have to have a whole bunch of these happen in order to even see it. So it's a single photon emitted by a single electron dropping down from the first excited state to the second. So what does that energy correspond to in terms of light? Because we know that light has frequencies, right? So what does the energy of light correspond to? Well, here's the thing. Now we're going to drop back in time again. So Niels Bohr is working on this thing in 1913. Rydberg worked in 1888, but smack in between them, Albert Einstein brought us a very, very interesting thing by studying what's called the photoelectric effect. The photoelectric effect shows how electrons are liberated from a metal if light shines upon them. And it was found that if the light, no matter how intense it was, if it was infrared light, it did not liberate the electrons. But as soon as the frequency was large enough, then the electrons would be liberated away from the metal and then they could move. So what this meant is that photons were acting like a particle, and a wave. That brings us back all the way to Newton's corpuscles of light again. Oh my goodness. Well, light has a duality of waves and particles. So here is now proof by Einstein in 1905, which got him the Nobel Prize, by the way, that the energy of a photon is proportional to the frequency, or inversely proportional to the wavelength of the light. And the transmogrification of frequency or wavelength into this particle concept of like how much billiard ball type particle is in the photon is by the Planck constant h. So energy of the light is equal to h, which is Planck's constant, times the speed of light divided by the wavelength, and that gives you the energy of the photon. Ha! But we just saw that the energy difference between the photon, that the energy dropping from the first excited state down to the ground state is 10.2 electron volts. And if we say that's the energy, and then we see what the wavelength works out to be, the wavelength works out to be 122 nanometers. Wow, okay. So when the electron drops from the first excited state down to the ground state, the energy is 10.2 electron volts. And that's converted into 1.22 times 122 nanometers, or approximately 1,200 angstroms. So now that we can plug in and look at that and see what the Rydberg number is, and we say, well, wait a second, what's the Rydberg value? Well, Rydberg value says that what's the wavelength? And we say, oh, n1, n2 squared. Wow, is this interesting? It matches Rydberg's formula exactly if you put in n1 equals 1 and n2 equals 2, which is just really amazing. So Rydberg's formula predicted it, or at least was empirical. Now we've got something that actually shows it. So the wavelengths that are predicted by Bohr's model of the atom are matched directly what Rydberg found in 1888. Just as another example, and a more pertinent one that we're going to talk about later, electrons can jump up multiple orbital levels and drop back down multiple orbital levels. Or it can go up and down and down and up and up and down and down and up, depending on what's happening in the environment in which it lives. So let's say that the electron, instead of going up only one level, jumped up 2 from the ground state to the second excited state, or n equals 3. So now it's in n equals 3, and let's say it's going to drop twice. So it's going to step down each level of the ladder on its way home to the ground state. So it's going to drop from 3 to 2, and then from 2 to 1. Well, we just did 2 to 1, which gives you an energy of about 10 electron volts. But let's look specifically at the one where it drops from 3 down to 2. All right, so 3 down to 2, we can calculate the energy of the two of them, and it starts for the third. This n equals 3 is the second excited state. I know, 3 is second, 2 is first, ground is 0. Oh, right? kind of really annoying, but let's work with it. So if we're going to start from n equals 3, the second excited state, and it'll be a little bit higher, a little bit closer to zero energy, about 1.5 electron volts in the hole. And the first excited state is 3.5 electron volts, 3.4 electron volts in the hole. And we take the difference of those. It's an energy difference of just under 2 electron volts, or 1.89 electron volts. We convert that using the formula that Einstein discovered in 1905 that got him the Nobel Prize, and we find that 656.3 nanometers. And if we look at that, that is Rydberg's formula for the transition between 3 and 2 in the Rydberg formula, and that is exactly the wavelength of light that is predicted. That's exactly the wavelength of light that you observe in a spectroscope. That is the transition in the red area of the spectrum. That is H alpha, one of the most common wavelengths of light to look at for all astronomical species, because most of the universe is made of hydrogen. And so when you look out at the Orion Nebula, which has this characteristic pink glow, and that characteristic pink glow comes from radiation, light being emitted specifically at 656.3 nanometers. We now know that's due, according to the Bohr model, to an electron dropping from the third excited state down to the second excited state, and then on its way back to the ground state, but it's actually gotten some energy from somewhere, and it's falling and cascading back through, and it emits this form of light, and there it goes, it's emitting this light. So now we know, we have a model for a very important thing, which is we now can model the spectrum of light. But let's take, before we go there, let's go into a little weird place, because we've had a very strange set of things. And Bohr's model of the atom assumes a little dot orbiting another little dot in a circular motion. But we've already seen that there's a certain way, but physics kind of went a little awry for us. And that model works extremely well for us, the Bohr model. But let's take it forward just a little bit to determine that that's not still the end of the story. Because electrons are not pure particles. Well, what was found in 1924 is Louis de Broglie, in his PhD thesis. He's a French physicist, and in his PhD thesis, he postulated that every subatomic particle, or more specifically, every particle has a wavelength. So he said that every particle, an electron, a proton, you, me, the chair, a building, a whole planet, the galaxy, it has a wavelength. And that wavelength we'll call the de Broglie wavelength. And we can take the concept of the energy of a photon, we convert, like just from Einstein's discovery, and we convert that into a momentum, because light, even though it has no mass, still carries momentum. So if it can carry momentum, and matter does carry momentum, this is where de Broglie kind of made the leap. He said, well, if light carries momentum and matter carries momentum, then we should be able to equate the two. So de Broglie said, well, what is the momentum of light given its wavelength? And so he said, fine, there it is. And so now you actually then put the weight, and then you establish then that there's also a momentum associated with an electron. And so combining his concept with general relativity says that there is a speed with which it's going, and if it's going greater than the speed of 0, then it'll have some sort of wavelength associated with it. In any event, de Broglie said that as electrons travel through space, they are not just particles, they're a packet of waves. And what's fascinating about this is this concept that every element, every subatomic particle, or every particle in existence has a wavelength, and we call it the de Broglie wavelength. This concept is experimentally verifiable. And in fact, in 1927, it was experimentally verified that electrons do diffraction just in the same way that light does. So electrons do diffraction, protons do diffraction, even large molecules do diffraction. This concept of the de Broglie wavelength is ubiquitous throughout. And apparently there's macromolecules that can even be shown what their de Broglie wavelength is and actually measure it. So we can measure the spread of a particle. That means it's not all in one place. It means it's not a pinpoint particle that you can say at the head of this pin, at the point of this pin, that is exactly where the electron is. You can't do that because it has a wavelength. Really weird. All right, so what does that mean for our model of the atom? We're going to kind of diverge away into it. We're going to say de Broglie said that wavelengths of light, wavelengths of electrons, if they're trapped, then they have a standing wave. And so he said, okay, fine, what's a standing wave? A standing wave is just like if you tie a rope to a doorknob and you flick your wrist up and down, you hold it, you can make various waves against it because your wrist is fixed and the doorknob's fixed. So you can make a standing wave, even though the waves are moving, they're in there, they're moving up and down like a jump rope, or you're doing all sorts of rope tricks, but the ends are fixed. They're not flapping around. The ends are fixed. So you can have standing waves, and the more energy you give to the standing wave, the more nodes there are to the wave. So we can then reformulate the Bohr model as having a pit. And so think of the Bohr model of the atom, and this is de Broglie's sort of version of it, or at least one way of thinking about it, using waves of electrons. So the bottom lowest energy is where it's only one wavelength. And the next energy level is 2 wavelengths. The third wavelength is 3 wavelengths, and so on and so on and so on. So the lowest possible energy state in an atom, it must have only 1 wavelength in a standing wave at the bottom of the pit. And so each one of these locations at the radius at which it is, it's not an electron circling like a little dot, a little planet circling a little sun. It's a standing wave surrounding the dot, which is itself kind of a wiggly thing too. So now we can think of it, instead of having it fixed on the doors, the ends must connect together. And so we have a circular standing wave, not a linear standing wave. You just take the end of the door and your wrist and put them together, and now you've got a circle. And at the bottom of the they must be circular waves, otherwise it's not going to be in the box. So only at these fixed locations where you have 1 wavelength does it work. And then we can equate the radius to the wavelength of using the de Broglie relationship, and we get the same exact result as Bohr did with his concept of the little planet orbiting the little sun. Now we say that the electron is not actually a point particle, it is a standing matter wave surrounding the proton, which means, where the heck is the electron inside the atom? That's a really interesting question. We can't find it because it's a wave. So it's a wave inside of there. And the de Broglie relationship then gives a very good explanation as to why this quantization must occur, because electrons have wave properties, and they must have fixed standing length wave properties inside of the atom in order for it to actually be bound inside of an atom. If it does not have if it's not a standing wave inside of inside there, then it's not going to be, it simply will not be a bound state. So unbound states are states that have more energy than they're more energy than being in the bound state, plus they don't have the right number of wavelengths. So you must have the circular standing wave inside the atom of some kind. So this concept, these two concepts, where we have the Bohr's relatively simple model of an electron spinning around as a ball, that works. But then we have de Broglie's relationship, which tells us something even new about the nature of matter. Both of them work and tell us everything we want to know about the spectrum of light, from the Lyman series in the ultraviolet showing the transitions up and down, the Balmer series in the visible light showing transitions up and down, the Paschen series, which is an infrared, which starts at level 3 or ends at level 3, n equals 3. And then we can then explain all of Kirchhoff's laws using the Bohr model of the atom. The lines that you see in Kirchhoff's spectra, an emission spectrum, is due to the huge numbers of atoms jumping up and down, electrons jumping up and down in orbits and sending light out from those in various directions, in random directions. There's no one direction that sends the light out, so it might as well go to you. And so the photons that you receive them at specific wavelengths, and therefore that's where we get the emission spectrum of Kirchhoff, which was an empirically derived idea. Likewise, absorption does the same thing, because as the light goes into the cloud of atoms, it absorbs specific wavelengths. It makes it a little darker at those wavelengths, and because that light's going someplace else. And so if you look through a cloud of gas, you're going to see that it's darker at those locations because some of that light has been absorbed and re-radiated in other directions, and that gives the emission spectrum from the side. So the Bohr model of the atom, and even de Broglie's model of the atom, explains Kirchhoff's empirically derived laws about the nature of what spectra are. So we have lots of different ways of talking about emission lines, absorption lines, and this leads us to the incredibly important idea that spectroscopy is the most key thing that we have in all of astrophysics. It is everything. Basically, we will be able to determine huge numbers of things about a location because of its spectrum. First and foremost, we can determine what elements there are by modeling the spectrum of it, by looking at exactly what we see in the light. We've got all this light here, we got coming in and out, emission, absorption, and so forth. But we can also determine temperatures and pressures because of the widths of the lines, because of the Doppler shifts. We can determine huge numbers of things from spectra. But it all comes from the very simple concept of the nature of the model of the atom. So let's actually just back this up a little bit, and we're going to take it away from the spectroscopy for just a second and go address something that I was looking at and kind of dodged around, but now I'm going to come at it full force. Okay, so where is the electron inside of the atom? So I alluded that there's some really odd ideas, and let's see what we get out of them. De Broglie's concept of a matter wave and having electrons be standing waves inside of the atom changes a lot of things about the nature of what we think about of atoms and matter in general. So de Broglie's hypothesis that matter is a wave fundamentally changed a lot of ways the way we think about things. So if the electron is in a standing wave inside of the atom, then where is it? Because just in the same way that we said, okay, we're going to hook the string up to a doorknob and to my wrist, we can easily make it so it's a nice standing wave. We can say, oh, well, what's the wavelength? Okay, we can get the wavelength of it. And if we flick it harder, we can have more nodes on that thing, and we can say it's a shorter wavelength. But if we then ask, where actually is the wave on the string, we wouldn't have a good answer. We'd say, well, I know that it's on the string. I know that it makes up the entire length of the string, but where exactly is it? Where can I pinpoint it on the string? And the answer is no, you cannot. So in the same sense, we now have a very strange thing where we cannot pin the electron's location inside of a bound atom. So once it's in there, it's in a standing wave setup. The standing wave does not permit us to actually find the location of the electron, and it gets worse from there. De Broglie's concept actually still kept Niels Bohr's idea of the little planet orbiting a little sun, but now we don't even do that. So now de Broglie said, okay, make a standing wave that's orbiting a little sun. Fine, but that's a circular pattern. And we now know by actually then taking de Broglie's concept and accelerating it a bit more and looking at it in 3D space, and actually that's the only way to actually look at it, is that we don't see it as a circular standing wave, but a spherical standing wave with spherical harmonics. And that's a very, very, very weird thing. And the solution to the equations of what the hydrogen atom really looks like had to wait until Schrodinger made his famous equation, the Schrodinger equation, which codified completely the concept that matter does behave as a wave. And so when we take this concept of the wave nature of light, of all particles, and filter this through the Schrodinger equation, we find that not only is the electron a standing wave going around it, but somehow it's somewhere on the surface of a sphere that has a certain radius. And so the Bohr radius is not just the radius of the orbit, it's the radius of the sphere that the electron seems to be in. And the actual radius itself is fuzzy, and where the electron is on there is fuzzy. In fact, it's not determined. We know its orbit, we know the most probable location of it, most probable location. And then we can actually say, well, where should it be in this place? Still applies the same thing though. If you actually give the electron a little bit more energy, it'll go up a level, it'll change its standing wave properties, it'll change its harmonic standing waves, but you won't be able to find the electron. And why won't you be able to find the electron? Well, take the proton and the electron and break them apart and turn them into an atom, not a bound atom, but have them be free particles. The proton itself is an extraordinarily small object. If you were to say that if we were to take the proton, which is on the order of 10 to the minus 12th meters. It's on that size. So it's it's a million times smaller than a micrometer, or a billion times smaller than a millimeter. They're really tiny things. So if you take a proton, and it's on the order of 10 to the minus 12 meters, and let's say we want to see how big the electron is compared to that. Well, let's blow up the proton, not from 10 to the minus 12 meters, but now let's make it the size of a mote of cigarette dust, cigarette smoke. A mote of dust, a single mote of cigarette smoke. That's a really tiny thing. It's just visible to your eye. And if we put that somewhere in a box, how far would the electron be in a bound orbit? We'll come back to the size in a second. So the electron is about, would live on the ground state on the surface of a sphere that's about 25 or 30 meters in diameter. So you've got this tiny, 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 tiny thing. And somewhere on the surface of a sphere that's 25 meters in diameter, that's where the electron would live. And the electron would live somewhere on that surface. It would have a fuzzy radius, so it wouldn't necessarily be right at that surface. It would be somewhere maybe between 20 meters and 40 meters. It'll be in between there. And so it would be a wave-type property throughout there, and you can't pin down where it is. In fact, saying where it is when it's bound as an atom doesn't really have a lot of meaning. It has a loose meaning. But really, we know the energy level of the electron, but even that is not well known. So the electron itself is a fuzzy object, and so is the proton, too. So the actual orbital radii are fuzzy, but it shows you the size scales. Think about the Museum of Natural History. Go to the Museum of Natural History in New York City. You find this enormous, huge sphere. Google the Hayden Planetarium to see the size of the sphere. It's really big. So there's a model inside the museum that says, here's the size of a proton and here's the size of an electron. It tries to show you the size of an atom. And basically, put the proton, this mote of dust, in the center of that sphere, and put the electron somewhere on the surface of that sphere. And that gives you the concept of how big it is. The electron itself is about 2,000 times less massive than the proton, but its size is determined kind of by its interaction. So it actually has kind of a very strange, it's very, very small. Its characteristic interaction is a little bit bigger, so its actual physical size is kind of an oddly ill-defined term. There are some definitions, there are ways to define how big an electron is, but it's a much smaller object than the proton. So the electron's orbit around the proton is fuzzy. However, we can approximate it with de Broglie's concept, which means it's to a circular orbit. And we can approximate de Broglie's idea to a little tiny planet around a little tiny sun. That's Bohr's model of the atom. And Bohr's model of the atom had a quantized set of, as a quantized angular momentum. And we still maintain this concept of the quantum mechanics. I mean, that's what we mean. The mechanics simply is how do things move under the influences of forces when they're given energies and speeds, and what are their locations, how fast do they go, how fast do they accelerate, how fast do they decelerate, etc. What are their directions change? That is mechanics. And it depends on their masses, it depends on their inertias, it depends on their momenta, it depends on all these things. And those are the study of mechanics. So quantum mechanics says what happens when you take classical mechanics, which is just how things move, but apply quantum principles to it, such as quantized angular momenta, like Niels Bohr suggested, or matter wave concepts, such as de Broglie came up with. Now, this idea the fuzziness arose, of course, from the Schrodinger equation, which is a relationship that just demonstrates how all of matter demonstrates wave-like properties. Even large-scale matter displays wave-like properties, although the wavelengths are incredibly short. When you're talking electrons, the wavelengths are roughly the same size as the particle itself. So now you've got a matter and a wavelength that are roughly the same size, and you have to deal with these quantum mechanical effects. We don't, in our daily lives, don't have to deal with quantum mechanical effects because our sizes are much larger than our characteristic de Broglie wavelengths. So this is kind of an important set of things. In fact, the quantum mechanical universe that we're talking about, the quantum mechanical model of the universe, is extraordinarily well supported by experiment. It is considered to be one of the triumphs of 20th century physics. And it had the evidence for this model that matter behaves in wave-like properties That's enormous evidence for it, such as the nature of the black body radiation. Einstein's photon and photoelectric effect demonstrates it. There's wave-particle duality, meaning the dual nature of both wave-like properties and particle-like properties, using, say, Young's double slit experiment, but you can use Young's double slit experiment for photons and apply it to electrons, and you get the same thing. So this was done in 1927, and this was characteristic proof of de Broglie's concept in 1924. Further and foremost, you can have electron scanning microscopes, which must do quantum mechanical behavior. But even more bizarrely is that every electronic device that is used today must take into account quantum mechanical effects in order to actually operate. And we'll even see that quantum mechanical effects are critical for our understanding of how the sun works. Without quantum mechanics, we would actually not have any idea how the sun actually shines as long as it does for the rate of energy that it puts out. Quantum mechanics is a requirement for us to understand the way that the sun works, and the predictions associated with it tell us how the sun works, which is a really fascinating thing. And so when we dig deeper into the nature of what quantum mechanics tells us, we uncover what we would call a bedrock principle. And some textbooks on quantum mechanics start with the concept of the non-commutativity of various parameters or various measurements. But we can summarize that with the Heisenberg uncertainty principle, which says you simply can't measure paired measurements. There's certain sets of paired measurements that you cannot measure infinitely accurately at the same time. Specifically, two of the most famous are you can't measure the momentum of a particle and the position of a particle with equal accuracy or with infinite precision. So if you know exactly where the electron is, you have no idea what its momentum is. And momentum, according to the Broglie principle, is the wavelength. All right? So if you knew exactly what the de Broglie wavelength was, you don't know where its position is. And that's exactly what we meant by the whole string wave on a string thing, is that if now the electron is a wave on a string between a doorknob and your wrist, and that's the electron, where is the electron? It's there, but where? So you can't find it. And that's a fundamental basis of quantum mechanics, is that you can't have these measurements. You can't have infinitely precise measurements of two things, of paired sets of measurements. So another one is the energy difference between states, and the time at which they live at that state, or the knowledge of the energy level of that state. And that's actually why the second one is actually why the lines have a breadth to them in spectroscopy. And that's a basis of a line. It's one of the bases of the lines. There's many reasons for the line's breadth, but the width of the lines can be attributed to the fact that we really can't actually know the energy level inside of the atom. So we say, oh, it's energy level 3 and energy level 2. Well, those energy levels are fuzzy. And so but the very act of the fuzziness itself creates a width to the line. So the frequency at which we observe it and is proportional. Cannot be. You can't actually measure both the energy of the output and how long it lives at that location, in that state, which is really fascinating. So the concept of quantum mechanics, the basis of it, is that there's these fundamental bedrock principles, and one of them is the Heisenberg uncertainty principle that says there are two separate measurements or paired measurements that cannot be measured with equal or infinite precision. You can't measure one of them without having complete lack of knowledge of both, of the other one. So you basically get fuzzy on these things. It's like, I kind of know it to this well, and I kind of know that one to that well, and that's all I'm ever going to get. And there's no thing you can do to circumvent that. That is a fundamental axiom of quantum mechanics. People say, well, if technology gets better, then they'll figure it out. Well, this is having been figured out. And this is how nature works, which really is weird. It's not something that'll be overcome by somebody building a new widget or something like that. No, this will never be overcome because it's a fact of nature. It's the way nature works, which makes it even more interesting. So So if we think about the nature of way nature works, we find that the solution for the Schrodinger equation for the hydrogen atom has all sorts of funny waveforms, and they're based on spherical harmonics and the appearance of the thing. So it's not these simple spherical orbits, these circular orbits. It depends on, there's actually three quantum numbers. There's the primary quantum number. We also have what was called the azimuthal quantum number, the magnetic quantum number, and they're kind of weird, but they're all interrelated, and yet these three quantum numbers, which are associated with electrons and matter waves, or waves of matter, because we're looking at 3 dimensions, we have 3 quantum numbers. I guess you can do it that way, but let's just keep it that for simplicity. But there are 3 quantum numbers that determine the appearance of the waveform of the electron as it orbits the proton at various energy levels, which is interesting. And some of those quantum numbers don't change the energy. The magnetic quantum number does not change the energy. They're degenerate, it was called, because they're the same energy, but they have different configurations. So we can have the same configuration at different configurations at the same energy. In any event, the hydrogen wave equation is the only atom for which we can solve the Schrodinger equation to actually give us the appearance, to analytically show with an equation what it is. Everything else is too complicated and must be done numerically. Finally, what's very strange, I already mentioned, it's like, well, what is your quantum wavelength? Well, it's true, is that if you could somehow, over an extraordinarily long period of time, live, let's say you could potentially live for 10 to the 70th years. Let's just say you could do that. That's a long time to live. If you could live for 10 to the 70th years, and every day you punched your hand at a wall, you just went pop, 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 punch your hand through a wall. At some point your hand would go through the wall. Not because you're punching a hole in the wall, but because the probability for you to do that, maybe you punched your hand at the wall 10 to the 12th times a second for 10 to the 60th years. It's a lot of times to punch a hand in the wall, and you're going to be doing like a super hummingbird. And so whatever, in any event, if you could do that, eventually your hand would go through the wall and come back because you're pulling your hand back through, and it will be okay. So the quantum mechanical world says that you can't necessarily know the position of things. And these are, when we talk about macroscopic objects like people, their wavelengths are incredibly small, so the probability that they go through things like that is catastrophically tiny, and so therefore you don't have to worry about tunneling through walls and things like that. But if we lived in a quantum mechanical world, then cows could go visit dolphins so long as the dolphin jumped out. A cow could then drop back as soon as it got back to the ocean. That's okay so long as the cow lands on the ground. Remember, the concept of quantum mechanics says you can't know the position and the momentum of something with equal accuracy. If we lived in a quantum mechanical world, things would be appearing and disappearing all around us. Trucks, buses, buildings, everything, other people, friends would just simply appear and disappear. We would have no idea where they came from or where they're going next. And that's the quantum mechanical world. It's like, well, what's the probability that you're going to see your friend over here downtown? You would not say, hey, meet me downtown at 6 o'clock. You'd say, well, what's your best chance you'll be downtown at 6 o'clock? You get, to calculate the joint probability of you and your friend being downtown at the same time. In any event, quantum mechanics is how we actually discuss the nature of the world. But when we talk astronomically, we tend to use the Bohr model of the atom because it's really simple to understand, and that kind of gives a really good visualization. It's very hard to visualize all these other things. So what we do is we try to think that we know that that basically electrons must live in fixed orbital radii away from their nuclei of their atoms. And that concept then leads us to the nature of what spectroscopy does and helps us to understand how Kirchhoff's laws arise. And so when we look at distant astronomical objects, as we will in the future, then we will see that we can model an atomic process to the light that gets emitted to what happens when it arrives at our telescope and our detector. So next time, we'll talk about telescopes and how they work. We'll see you soon.